principal madam, Dr. Devi. Dr. Devi, uh, welcome you, ma'am. Then
Thank you, sir.
I
Thank you.
wish to welcome, Dr. Viri Satyaranayana, Professor Electronics and Communication Engineering, Sri Vidyaniketan Engineering College, Tirupati, who is going to present the session one, bio-inspired algorithms for optimization. Welcome you, sir. Next, I want to welcome another guest, Dr. N. Alivelumanga, Associate Professor of ECE, Chaitanya Bharati Institute of Technology, Hyderabad. Welcome you, ma'am. Then I taking much pleasure to welcome all the participants from various institutions and our own colleagues to attend the program. Well, thank you for giving me the opportunity to address the welcome. Thank you very much.
Thank you, sir. So now about the program. So this webinar focuses on distributed computing and examines the opportunities, current state of the art, the challenges and future outlook to create autonomic distributed system with bio-inspired algorithms. It also continues to focus on bio-inspired autonomic distributed system. In addition, it expands its theme to cover a general class of algorithms that exhibit self-properties like self-configuring, self-organizing, self-managing, self-healing, self-scaling, and self-adaptive properties in the context of distributed computing. And some well-known bio-inspired algorithms include artificial neural networks, evolutionary algorithm, swarm intelligence, artificial immune system, cellular automatic algorithm. And they have been successfully used as an alternative and superior solution to the problems that traditional algorithm cannot solve satisfactorily. So we focus on this bio-inspired algorithm today. I would like to thank our management and our chairman and our principal, Dr. M. Devi ma'am, for giving permission to organize such a kind of webinar today. And this program consists of two sessions. So in the first session, Dr. V.V. Satyanarayana sir, Sri Vidyaniketan Engineering College, Tirupati, will going to handle this bio-inspired algorithm of session one. And after lunch break, the session two will be handled by, that is, methodologies for power optimization by VLSI design. Will be continued by Dr. N. Alavelu Manga ma'am, Associate Professor ECE of CBIT Hyderabad. And I'm sure that you will all have a field that is enriched with knowledge after completion of this webinar. And I welcome you all once again to the seminar and hope that you will have a good, great time ahead. Now I request our enthusiastic leader of our institution, Principal Dr. M. Devi ma'am, to felicitate this online gathering. Please, ma'am.
Thank you so much, Ma. So, on behalf of the entire fraternity of Vivekananda College of Technology for Women, I once again welcome Dr. V.V. Satyanarayana, Professor, ECE, Sri Vidyaniketan Engineering College, Tirupati, and Dr. N. Alivelu Manga, Associate Professor, ECE, CBIT and Hyderabad. Thank you so much, ma'am, and thank you so much, sir, for accepting our invitation. And you are here today to give webinars on the following topics, that is bio-inspired algorithms for optimization and methodologies for power optimization in VLSI design. So basically, I am from civil engineering, but I am totally new to this topic, and even I am also eager to hear the inputs from you. So thank you so much for readily accepting our invitation, and I wholeheartedly appreciate the Department of Electronics and Communication Engineering for arranging such a kind of wonderful guest speakers, and I am so happy that you will be utilizing this opportunity well. So kindly extend your fullest cooperation and gain as much knowledge as possible during their presentation. And my warm welcome and thanks to the outside participants also. So thank you so much, and I once again welcome you all. Thank you and welcome.
Thank you, ma'am. About our chief guest. So Dr. Satyanarayana sir is currently working as a professor in the Department of ECE, Sri Vidyaniketan Engineering College, Tirupati. Sir has completed his PhD from Jawaharlal Nehru Technology University, Hyderabad in 2015. His main contribution in research is towards improvement of recognition systems. His research provided to recognize the input in 3.1 seconds, which is far better when compared to the existing benchmark techniques taking 31 seconds to recognize. One of his research paper entitled Multi-Level Network Security based on iris biometry is listed as iris image quality, and this reading material by NIST laboratory under US Department of Commerce. He has 14 years of teaching experience, and the sir has published 28 papers which are indexed in Scopus and has 2 patents to his credit. He is the reviewer of IET, Image Processing, and other Scopus and SCI indexed journals. He is currently working on optimization techniques for improvement in classification over the real-time problems. So, on behalf of entire Vivekananda College of Technology for Women, it's an immense pleasure to welcome our beloved chief guest, Dr. Satyanarayana, sir. We welcome you, sir. Sir, shall we start the session, sir? Sir, shall we start the session, sir?
Yes, madam. Yes, madam. Can we take it now?
Yes, sir. Yes, sir.
Yeah, is it visible, madam?
No, sir,
Hello?
we can't able to see, sir. Yes, sir, it is
not
visible.
visible.
Yes,
Yeah,
sir, it
yeah.
is visible.
Yeah, good morning, one and all. And in this session, we are going to talk about bio-inspired algorithms on a research perspective. And I am Dr. Satyanarayana, working in Vijayaniketan Engineering College. So this is my outline, and we'll be talking about 2 algorithms mainly over here. That is the particle swarm optimization and cuckoo search algorithm. Along with that, we will be seeing some of the MATLAB examples, how you are going to apply. Along with that, on the side, you will be seeing the illustrative examples, that is the numerical examples, how to solve these things. So the first thing here is that you will be having a question that why you require some optimization. Basically, we'll be having some certain inputs where these inputs will be relating to, or will be processing those things to get some outputs. We need to choose these inputs appropriately in such a way that these inputs will cater to the best outputs. For that reason, we require some optimization that need to be carried out so that the best and desired output is achieved. Okay. So we'll be allocating the resources, and after that we'll be designing based on these resources. We'll be designing the terms, and these resources will be allocated in such a way that we'll be designing the characteristics such that optimal characteristics are achieved and the control characteristics are being designed for that. For that, we'll be having 2 types of problems, that is maximize or minimize. So we'll be defining the objective functions in such a way that there will be, yes?
Sir, excuse me, sir. Screen is not visible, sir.
Now is it visible, madam? Hello?
Yes, sir. Now it is visible, sir.
So here we'll be allocating some resources so that to carry out some design, and this design will be leading to some optimal characteristics, and we'll be controlling that one. So how you will be controlling? You will be controlling the objective function such that it may be a maximization problem or a minimization problem, and we will be setting some boundary limits for that one. So these are the boundary limits that need to be set while going with the limits. So for example, let us consider a hyperbola of this case where this X will be given as the input, such that we will be choosing the X such that we will be maximizing the point Y. So we will be choosing the best out of that one such that Y is maximum. This is a simple case where you can choose it directly. You can solve this problem also by using some derivative methodologies. So based on these things, some complicated problems can also be, complex problems can also be solved. So this is how you will be solving some optimization. So we will be writing some optimization algorithms in the next slides, where you will be seeing some optimization algorithms and the applications of these optimization algorithms. The first one is the warehouse placement. So you will be having some different locations where the warehouse need to be placed such that the minimization of the shipment time is the required one. So you need to choose an optimal location for the warehouse placement such that the shipment time will be minimum, so that the shipment cost reduces, henceforth making the resources to be optimally utilized, such that the desired characteristics of the design, whatever you are going to design, that is the pathway for the shipment, will be achieved. And after that, you will be controlling the things from there. This is one best example for that one. Next one is construction of a bridge, where the design need to be optimal such that the maximum load bearing capacity of the bridge need to be achieved. This is another application. And the next application is all we know, the strategical games what we are playing now. So within the given limited time, you need to build your army so that the army strength is maximized. So your build order must be in such a way that the maximum strength need to be achieved. So we cannot have a particular set of army people where the strength is very less, but we need a group of people. How to select such group? How many people are required? This is one strategical game where that optimization is also useful. So this is another example. And next one is artificial pancreas, where the delivery of insulin need to be maintained in a proper way such that it reduces the blood sugar deviations. If it is high, obviously the sugar level reduces so that the person or the patient who is there will get weak. If it is not delivered properly, the blood sugar may increase. So what is the optimal level? That it has to be set out. That is the main objective function over here. And the next one is aeroplane design. The wing design must be in such a way that the weight must be minimum, but the strength must be high. So this is another optimization problem where you need to maintain the weight as the minimal value, but the strength must be a higher one, so that the wing must have a long durability, and with less weight it can be handled by the plane while it is under the flight. So these are the optimization problems that you will be having. So yeah, and we'll be going to the first one, that is the particle swarm optimization. So here the particle swarm optimization is a nature-inspired evolutionary, and it's a stochastic optimization technique. And this is a technique that is used to solve computationally hard optimization problems. So in computational science, particle swarm optimization is a computational method that optimizes a problem by iteratively trying to improve the candidate solution with regard to a given measure of quality. So it solves a problem by having a population of candidate solutions, here dubbed particles, and moving these particles around in the set space according to a simple mathematical formula over the particle's position and velocity. And each particle's moment is influenced by its local best known position, but also it is guided towards the best known positions in the set space, which are updated as better positions are found by other particles. And this is expected to move the swarm towards the best solutions. So, and the PSO is a robust stochastic optimization technique. Here, the robust means it is able to solve multiple types of problems, and it is known for its quick and easy implementation. And this was developed by James Kennedy and Russ Everhart in 1995. And this was first intended for simulating the social behavior as a stylized representation of the movement of organisms in a bird, like the flock or a fish. So the algorithm was simplified, and it was observed to be performing optimization. And the book they have written, that is Kennedy and Eberhard, they describe many philosophical aspects of the particle swarm optimization and swarm intelligence. And PSO, you need to understand that clearly this is a meta-heuristic algorithm. So what do you mean by meta-heuristic? So in computer science and mathematical optimization, a meta-heuristic is a high-level procedure or a heuristic design to find, generate, or select heuristic. That is a partial search algorithm that may provide a sufficiently good solution to optimization problems, especially with incomplete or imperfect information or limited computation capacity. So meta-heuristic sample is a subset of solutions which is otherwise too large to completely enumerated, to be enumerated or otherwise explored. So meta-heuristics may take relatively few assumptions about the optimization problem that is being solved, and so may be usable for a variety of problems. Compared to the optimization algorithms and iterative methods, meta-heuristics do not guarantee that a globally optimal solution can be found on some class of problems. This is very, very important, and many meta-heuristic implementations, some of the stochastic optimization, so that the solution found is entirely dependent on the set of random variables that are generated. So in combinatorial optimization, by searching for a large set of feasible solutions, meta-heuristics can often find good solutions with less computational effort than optimization problems, iterative methods, or simple heuristics. So as such, there are useful approaches for optimizations. So most of the things we'll discuss now, and these particle swarm optimization can be used, can be applied successfully to a wide variety of search and optimization problems. So PSO has been built by abstracting the working mechanism of the natural phenomena, like that of a fish or birds, that is the swarms are taken into consideration. Specifically, it was inspired by from the swarms in nature, such as the swarms of birds, fish, etc. In PSO, a swarm of n particles, that is the individuals what we are taking over here, communicate either directly or indirectly with one another using search directions. So you will be considering those search directions, what we will see now. The algorithm uses a set of particles over the set space to locate the global optimum. So during the iteration of these particles, each particle will be updating its position according to the previous experience and the experience of the neighbor. So it will be considering not only its own experience, but also the others' experience. So you will be having three vectors over here. So first one is the position vector, that is the location, and next one is the velocity vector, and through which you will be calculating the local position vector, that is the p vest, that is the particle vest. So three vectors: x vector, which records the current position or the location of the particle in the search space. Next one is the velocity vector, that is the direction of the particle through which it will be traveling if undisturbed, provided. And another one is the p vector, that records the location of the best solution found so far by the particle. So this is the one. Now consider an example for this one. Let us consider 5 particles over here, and each particle will be having a velocity vector that is being defined by this. So this is the velocity vector, and each particle will be having that velocity vector. So these particles will be moving towards some direction based on the conditions that are being defined by the initial parameters. So you will be having a local best position where this velocity will be resulting in. So this particle will be moving in this direction, so that it will be moving towards the local best position. And each particle will be moving to its own known local best position, such that it will be achieving the global best position. This is the one we need to understand. So each particle will be moving towards the local best position based on the velocity vector that is being taken care. Okay, and after achieving this local best position, it will be moving towards the global best position. Likewise, each and every particle will be having its own local best position, so that each particle will be moving towards the global best position. So this is how all the particles will be moving towards the global best positions. So if you clearly understand this one, so each particle will be moving towards the global best position. So this is the one. So now, when compared to GA, you can will have a question that what is in contrast to the generic algorithm, where GA has the selection operator, but there is no selection operator in the case of the PSO. So PSO does not implement the survival of the fittest strategy, and all individuals are kept as members of the population throughout the operation in the PSO. This is the difference. Now, considering the algorithm here, so here, when you start the algorithm, we'll be initializing the swarm with a random position x0 and velocity vector v0. So these are the two vectors what we'll be defining here, and we'll be taking these two as the initial vector, and we'll be obtaining this from the random numbers by generating some random numbers. And considering each and every particle, let us say in the previous case we have considered 5 particles. So each and every particle we will be considering it. So 5 particles we will be considering. So each and every particle we will be evaluating the fitness. Whether it depends on the maximization or the minimization function what we are taking. So f of x, let us say I have defined f of x equal to some value x1 square plus x2 square plus 2x1 x2 minus 5, like that. So if I want to maximize that function, we will be evaluating that, maximize the value when you substitute the x1 x2 variables. So if the fitness function, the determined fitness function is greater than the global best, then global best will be modified. This is the one. And if the fitness function is greater than that of the local best, then P best will be modified. After that, this is the terminate condition. This is the terminate condition where you will be terminating it when all the particles achieve the similar values. When all the particles achieve the similar values. If all the particles are not achieve the similar values, then update the velocity. Okay, update the velocity of each and every particle. Then update the new position, where you will be calculating the new position of each and every particle, like that of the previous case what we have seen over here. So from here P1, from starting here approximately P1 came out to here. So every time you are updating each and every iteration, you will be updating the particle position. You will be updating the velocity. So velocity vector is by taking this condition. So this tells the random variable that is being considered over here, and the P best minus xt, and this is the difference between the P best and G best. So here, and the next particle is considered over here, and again the fitness. This is a heuristical. So where when all the particles achieve the similar values, the terminate will be applied. So you will be terminating that one, so that you will be achieving the output as the global best. So this is the one where you can apply your own objective function, where you can evaluate a number of algorithms that you can deploy. You can modify the velocity part over here, and you can also modify the position part. Some research can be carried out over here, where anyhow you cannot do anything over here because you will be initializing. But here also, if you want to add some more initialization parameters, you can add up such that the objective function can quickly converge. Let us say for this algorithm, it is converging for let us say for 1,000 iterations. Now you can design in such a way that the parameters can be chosen in such a way that you can converge it within less than that one. So this is the area where you can concentrate for some change, so that you can develop your own algorithms for better results. Where G best is the global best position, and P best is the self best position, and C1 and C2 are the acceleration coefficients, and W is the inertial rate. And these two are the main parameters which determine the capability of the algorithm and how fast you can make it. Okay. So the basic concept of the PSO lies in accelerating each particle towards the best position found by it so far. That is the P best. So each particle will be accelerating towards the local best and towards the global best that is obtained. This is achieved by random weighted acceleration that is applied at each time of this step. This is done by simply adding the vector, that is the velocity vector, and the position vector to get another position vector. So once the particle computes the new location, then it evaluates the new location. If the new location fitness is better than the particle fitness, then P best will be updated. Okay, this is how the calculation goes on. And there is another simple thing, that is, see here, if I consider a particle which is having a particular velocity component in this direction, and the known best G best, that is the global best, and the particle best, which is nothing but the local best. So each particle will be moving according to the velocity, such that it will be moving towards this side to achieve the local best. But the particle local best need to be changed. So this is the one, it will be moving such that ultimately it will be moving towards the global best position. So this is nothing but psychosocial compromise, where you'll be moving somewhat, sometimes towards some part towards the velocity vector, some part towards the particle local best, and some part towards the global best, ultimately reaching the global best. So where the velocity component formulation is given by this formula, and this is the difference between the P best and G best, what you are considering over here. And this is a distribution, what you are taking over here, a random number. Based on this random number, you will be choosing that one. And the initial parameters that you are considering here is the swarm size, position of the particles, velocity of the particles, maximum number of iterations, how many number of iterations you require. And you will be considering the important parameters, that is the global weight. And if the W is larger, considering W is large, you will be having a good global search capability. W is large means you will be having a good global search. If it is small, the local search will be more. Local search. So it will be identifying the global best or P best based on the W. So adaptively you can choose that one. But this is not included over here, but you can make it adaptive so that it will be choosing the best pathway, like that of this one. Okay, rather than going this side and this side, I have made some social compromise over here, where the particle, every time the iterations, it will be moving over here. Rather than that one, you can take a direction like this, so that it will be moving towards this one. And another control parameter is the acceleration coefficients, where these C1 and C2, where if C1 is greater than C2, global best position, greater global search capability will be achieved. And if C1 less than C2, greater local search capability will be achieved. These are the two parameters that need to be considered. That is the inertial weight. Next one is the acceleration coefficients, C1 and C2. These are the two coefficients that you need to consider over here. So now I am considering an illustrative example over here to find the maximum of the function, that is f of x over the given interval -10 to 10, and using the PS2 algorithm. And I will be using 9 particles with initial position x1 -9.6, x2 -6, x3 equal to -2.6, x4 1.1, x5 0.6, likewise. So now I will be showing you 2 to 3 iterations. After that, we will be going with the final one. So now we have chosen the particles based on this one. So this is the objective function which need to be maximized. Okay. Now I've taken the particles x1, x2 up to so on x9, where the initial population, I have taken the initial number like this. So xi, where there are 9 particles over here, and this is the iteration, right? So x1 0, I have initialized the values. And after that one, I will be evaluating the objective function by substituting these values there, so that I will be getting this objective function. So maximum of this one, all the values, if you compare all these things, the maximum of the values like that of -120.16, -46, 0.24, 13.29, 22.64, and this is the maximum value till now. Okay. 26.21, and of course this is very much near, but this is small when compared to this one. So so this is the maximum value that I have achieved till now. So let us consider these C1 and C2, which are random. That is 1. You can choose any number. So and the initial velocities are set to 0. for the first initialization. So based on the iteration number, now we'll be going to that one. So we'll be choosing the best P best particle if it is greater than P best, or if it is less than or equal to P best. So you'll be changing the P best value if it is greater than that one, maximization. So P1 best, so this is the one, we have calculated the P best by this one. So P best is calculated, so you have got this one. Okay, so this is the P best value from the initial input what we got. So minimum of P best is nothing but 2.3. So the G best is 2. This is the one. So based on this one, I have got the global best formulation. Now considering the random numbers in the range of 0, 1, again R1 is defined. This is a random number 0, 1 random of 0, 1. If you apply it in MATLAB, you will be getting this one, and I will be finding the velocities based on the previous formulation what I have shown. So P best minus XIT and G best minus XIT. So this is when you apply this one, you will be getting the again the velocity vectors, new velocity vectors V1, V2, V3 up to so on V9. Again, after that one, you will be calculating the new position values. Anyhow, you will be updating the new positions where X1 is this one, X1, X2, X3, X4 up to X9. You will be evaluating those values. So again, you will be based on these X values that are being determined. You will be identifying the maximum values, objective function. You will be fitting the maximum. Where now again, if all the values are similar, and the difference is very much smaller, the criteria will be stopped, or else the step will be moving again. Okay, and again you will be finding the best objective function, that is the best fit function over here, from which you will be calculating. Again, you will be all the values are not similar, so you will be calculating again, and you will be going to the next step, such that you will be determining the P best values from this one. So again, you will be calculating the same thing. After 2 to 3 iterations of this one, again, in the second iteration, you will be updating the velocity, and you will be calculating the velocity for the 9 particles, and you will be updating the new position vectors, and again you will be calculating that one. And if all are not similar, so here there is a long gap over here, all are not similar. So again, the step will not be terminated. Again, you will be calculating the terms, and this process repeats until you get the maximum value. So this process stops whenever the maximum is achieved. Okay, all the values are similar. Okay, and now consider another example. Let us say in this case I have taken the objective function like f of x equal to 1 plus 2x minus x square, and the control parameters that I have defined here is 0.70 and 0.20, 0.60, and have only taken 5 particles here rather than when compared to the 9 particles in the previous case. And I have taken only 4 iterations for simplicity, and I have defined the random variables like this for each of the particles, 5 particles, R1, R2, I have defined, and these are fixed throughout. I have defined these as to be fixed throughout my computation for simplicity. But in reality, these can also be varied. And after iteration 1 and 2, I have achieved the global best position and the local best positions like this. These are the iterations that were carried out here in this case. So when you clearly see this one, the main advantage of PSO is that PSO algorithm is a derivative-free algorithm, and it is easy to implement. So it can be applied both in scientific research and engineering problems. It has a limited number of parameters, and the impact of these parameters to solutions is very small to other optimization techniques. And it is very simple, and which ensure the convergence and the optimum value of the problem, and it will be calculated easily within a short time. And PSO is less dependent on the set of initial points, because every time you will be defining the random variables there. That's why it is less dependent on that one. And when compared to the other optimization techniques, the main problem with PSO algorithm, this suffers from partial optimism, which degrades the regulation and the speed and direction. And in the first case, what we have seen, if we observe, it looks like all the function values nearly converge, but it is not converging. and the problems with the non-coordinate system like energy, field, etc. Now let us see some of the practical examples over here. This is the one. Now I'm using this function, that is particle swarm optimization, where the particle swarm is an inbuilt function that is existing there, which takes input as the cost function and the number of variables and the minimum variance and the maximum variance along with some options. So here I'm using this problem for clustering, and let us run this so that and the clustering is achieved. And these are the indexes. Yeah, these are the indexes that are being clustered over here. And another example, let us see, considering an image. I'm considering an image over here, test.png, and I'm clustering it based on the particle swarm optimization again, and the maximum iterations I have taken. Okay. And I have used the inbuilt function over here, where by using this particle swarm, and I'm running it now. If you see, the best function will be reducing. So I have taken the minimal value over here to minimize that one. So all the particles will be minimizing that one. So it will be reaching some minimal value, and then after that, it will stop. So if you clearly see, it has taken, it is also used for clustering. It has clustered this one and this area and this area. Actually, this is the original figure with some different colors. Okay. So when you see this one, this has been marked with some color, and this particular part or area is of one color. So that's why it has been clustered or grouped into one, and the region, another region. Likewise, it has been marked. So this is how you will be using it for clustering. Another example we will see over here. Where I am taking another this one. See here, this is the one where the objective function is defined by this one, u minus 20 square plus v minus 10 square, and I have defined the swarm initial position as this one. Okay, swarm initial positions and initial velocity I have defined, and the maximum possible value I have defined, and all these were defined. Number of swarms were 5,000, and if I run this one, you can clearly observe the particles are moving such that you can clearly observe the particles are coming nearby to achieve the global best position that is being carried out. Okay, here in this particle swarm optimization technique. After 5 to 10, after 5,000 iterations, you will be seeing that it will be getting converged. So after that, anyhow, it will be stopped. Okay. Next one, let us see another example over here. See, this is the output of the clustering that I have done on an image, where you can see the color that is being marked over here, where you can classify the particular area of the image into some regions. You can also apply the same on the blood images to classify some types of cells in the blood. You can classify. So this is how particle optimization is being applied on the images. Okay. So the next algorithm, what we are going to define here is the cuckoo search algorithm. So normally this algorithm is inspired by the behavior of the cuckoo, by the obligate of the broad parasitism of some of the cuckoo species by laying their eggs in their nest of other host birds or other species. Some host birds can engage direct conflict with the intruding cuckoos. For example, if a host bird discovers the eggs that are not of their own, it will either throw these alien eggs away or simply abandon its nest. So like that of, let us say, I have taken 5 particles. In that 5 particles, 1 particle does not belong to the group. What we will be doing here is that we will be discarding that particle, or else we will discontinue the search. This is the actual for our understanding. So here the host bird will be doing that. So it will abandon that nest and build a new elsewhere. So we will be leaving that particles over here. So in operation search, cuckoo search is an optimization algorithm, and it was inspired by this obligate broad parasitism of the cuckoo species. So some of the species, such as the New World broad parasitic tapera, has evolved in such a way that the female parasitic cuckoos are often very specialized in mimicry in colors and pattern of the eggs of a few chosen host species. So cuckoo search idealized some such breeding behavior, and thus can be applied for various optimization problems. So here the cuckoo search uses the representation like this. Each egg in a nest represents a solution. Each egg in this represents a solution. And cuckoo egg represents a new solution. You need to remember that one. So the aim of this is to use the new and potentially better solutions that are nothing but the cuckoos to replace the not so good solutions in the nest. So again, each egg in the nest represents a solution, and the cuckoo egg represents a new solution. So the aim here is to use that new and potentially better solution which is being given by the cuckoo search to replace that not so good solutions in the nest. So in the simplest form, each nest has one egg. The algorithm can be extended to more complicated cases in which each nest has multiple eggs representing a set of solutions. So cuckoo search is based on three idealized rules. First one is you need to understand that each cuckoo lays one egg at a time and dumps its egg in a randomly chosen nest. Second one is the best nest will with high quality of eggs will carry over to the next generation. Third one is the number of available host nests is fixed, and the egg laid by the cuckoo is discovered by the host bird with a probability of PA. This PA is chosen such that it belongs to in the interval 0, 1. So with that probability, it will be going. In this case, the host bird can throw the egg away or abandon the nest and build a completely new solution. So this is the one. So now let us see. So there are three different operations that are being carried out here in the evaluation process of the cuckoo search. First one is the Levy flight. Using Levy flight, you will be identifying the new solutions for the nest. So what is the Levy flight? So a Levy flight is named after the French mathematician Paul Levy. It's a random walk in which the step lengths have a Levy distribution, or that is nothing but a probability distribution that is heavily tailed. So Levy distribution is a continuous probability distribution for a non-negative random variable. So this distribution with frequency as a dependent variable is known as van der Waals profile, like that of a probability distribution function, which will be varying. It's not a Gaussian, but it will be like that of a simple Gaussian of this form. So it will be having this shape over here like this. It will be varying. So this is Levy distribution function. So this Levy distribution function. So the term Levy flight is used for one specific definition of the distribution of the step sizes. So we term this Cauchy flight for the case where the distribution of the step sizes is a Cauchy distribution, and you can see clearly some of the image processing people can call it as a Rayleigh distribution as well. So and the Rayleigh flight where the distribution is normal. Here we are considering it as a normal distribution. Remember that this is a normal distribution function. This is a simple normal distribution function. For that, you will be using RANDN function, which is there in MATLAB, where the values will be ranging from 0. So here, this normal distribution is not a heavy-tailed probability distribution, right? So Levy flight will be providing you the new solutions every time. New solutions will be derived using Levy flight. After that, when these new solutions have been attained, replace some nests with the new solutions. How you are going to replace the new solutions? Using this greedy selection strategy. What is this strategy? How you are going to replace? We'll see now. Okay. So now Levy flight. So we are going to generate a new solution based on the existing known values. So it is used to generate a new candidate or the solution, that is the x, by perturbing the current x. So new x value, we know this value, and we will be generating this random variable multiplied by the c value, where this C value is this one. So every time X new will be X plus random number multiplied by 0.01 multiplied by S, where S is also a random number that is being chosen, into X minus best value. How this best value is chosen, I'll let you know. Okay. So this is how it is being calculated. Okay. So now this S is a random step and is generated by symmetric Levy distribution, where it is given by this formulation U by V, where beta equal to determined by 1.5, and U and V takes the normal distribution with mean 0 and variance defined by sigma U and sigma V, where this sigma U, sigma V and sigma U are again calculated by these two formulations. So given the random variable, given the variable X, we are calculating the new value, and we will be calculating for the best value from this new. Whether it is best fit or not, we will be checking it every time. So the next step after calculating this one, after finding the Levy flight solution from this one, when the new solution is perfect or not, we will be replacing with the previous one. Under it, the host bird can throw the egg away or abandon the nest with a probability PA. Normally, in this case, what I have considered here is PA equal to 0.25. I have considered it as 0.25. You can consider any value. Okay. Generally, it is considered like this. And build a completely new nest based on this PA value. How it is being considered? Choose a random value R such that it will be lying between 0 and 1. It will be lying between 0 and 1. If it is less than this PA value, then only modify it. If it is greater than this one, if this is a contradictory, if this is not done, keep the X value as intact. Keep the X value as intact. This is the next. So if it is less than this one, then identify two random numbers, D1 and D2, then calculate the new X value. So X new equal to X plus random function of XD1, XD2. So these D1 and D2 are calculated initially, from which vary from 1 to n. Okay, this is how the new solutions are being carried out. Now, considering one new simple numerical example over here, we want to minimize this function, that is f of x equal to x1 square minus x1 x2 x2 square plus 2x1 plus 4x2 plus. Anyhow, here we are having only two variables where these two are bounded by these values, minus 5 to 5. So we need to have a value which is between minus 5 comma 5. And this cuckoo's parameter setting is now being set over here by using randomly chosen swarm population. I have taken it as 5 variables I have taken, and the number of iterations I have taken it as that is the population, that is 20, and the PA value to be 0.25. You can choose any number of iterations based on your application, based on the objective function. Here, as I have taken only 2 over here, I have taken this one. You can take a complex problem as well. So now, randomly initialize the food source such that between minus 5 and 5. So here X will be, the lower bound is minus 5. Anyhow, random value you take down, any random value such that random value and multiplied by this one. So that let us say 0.1 or something into 10 likewise. So you can calculate any random value. So that I have taken some value over here and I have achieved these values, x1 and x2. So my task is minimization. Now, as I have achieved x1 part and x2 for 1, 2, 3, 4, and 5, as the population I have fixed over there as 5. Here I have taken it as 5. So I have taken 5. So here, as I have considered it over here, now I will be calculating this f of x by substituting these x1, x2 values back in this objective function f of x, such that you will be writing down what is the f of x value. So here the main function is to minimize f of x. So I have achieved the minimal value of the function over here. So these are the best fit values where the minimal value is this one. Again, I am calculating s value with this sigma value, and I have taken this one as a beta as 1.5 and 0.6966 I have achieved. So this is the minimum value. So the best solution over here is minus 1.005 with minus 2.6027 with x1 equal to this one and x2 equal to this one, such that the achieved minimum is 4.9626. Okay. So I have achieved this one sigma value and the best value. So for the first nest, I will be calculating u value and v value, and again I will be calculating the s value. Because this is not the minimum value, so again I need to update it. So x new equal to x plus normal random variable multiplied by 0.01 into s into x minus best value. Again I will be calculating it such that I need to update this value. Every time this will be updating the value. So x1, x2, I am calculating it. Now, based on this, x1 equal to 4.5861 plus random number I have generated 0.8468 multiplied by 0.01, and s value I have calculated from here minus 1 point for x1, as I am calculating for x1. So I am taking this one x1 and I have placed over here, and minus 45861 minus 1 point this one. This is the best value. So x minus best. So I have got this one, which is small when compared to this one. Okay. Again, I have calculated. Similarly, I have calculated x2, and I have got the value 9554, which is small. And after this, again I need to substitute these x1 value and x2 value in the f of x function, such that I will be computing, I will be deciding whether these two values are correct when the value over here is greater than that one. So the obtained value must be less than this value. So because the function is minimization function, so the obtained value must be minimum when compared to the existing one. Then only this value can be updated. So I have calculated this one by using greedy selection, and if you see here, the new f of x that is being computed over here from this one is 63.4556, which is less when compared to the 65.0885. So this need to be removed, and you need to update it with minus 4.4946 and 3.9554. These are the two values with the f of x value 63.4556. Similarly, you need to apply for nest 2, nest 3, nest 4, and nest 5 as well. So after updating the solutions, I have got these values. Minus 4.946 with all these updated values. When compared to this one, 65.0885 is 63. When compared to the previous case, 37.1741, it has remained like that. And 41.593, 41.55, 22, again it is 21. 4.96 I have achieved here, it is 4.96. So again the best solution remained like this. So again we will be updating it, but after taking the random variables. So after first iteration of the first step, the host word need to throw the egg away. Rather than throwing away, what we will be doing here is we will be choosing the random variable such that it lies between 0.1, and we will be selecting R in such a way that if it is less than PA, X will be selected and modified. And again, based on these two formations. Now let us see for the first nest, I have chosen randomly these two. These two are randomly generated one. So here D1 and D2 are also selected. Here D1 is 1 and D2 is 3. These are also randomly chosen. Since 0.9732, sorry, this is 9732 is greater than 0.25 as per the previous example case over here. If it is R less than PA, then only you will be modifying it. If R greater than PA, no need to modify it. So here in this case, if it is as R greater than PA, so no need to update this X1 value. Keep it intact. And if it is less than 0.5, update. So what is the update value again? Minus 3.9554 plus random number. Okay. XD1, this is the one. And D2 is 3. What is the X value at the third position? This is the one. You need to take down this one. So here you need to be cautious while calculating these conditions. So based on this random number, again, the values will be changing. Okay. Here I have taken D2 as 3. That's why I have marked it as 4.3220. So the next new position is 3.9497, which is less when compared to. So the new position is 9497. Now calculate this fx value and identify whether it is obtaining the minimal value or not. Then only you can replace this one with the new one. Again, you will be choosing the greedy selection, and I have computed the new value, wherein I have obtained 63.3630 by substituting these new values there, which is better when compared to this one. So I will be replacing these values. I will be striking of this one, so that you will be replacing that with minus 4 point this one. With this, you will be writing this one and writing this new value over here. Replace this one. Similarly, you need to calculate for all the nests 2, 3, 4, and 5. So at the end of the first iteration, these are my updated values of x1, x2, and f of x. So here, this will be converging only when all the values achieve some similar value. At the end of the first iteration, I have got this one. At the end of the fifth iteration, I have got this value. At the end of the 10th iteration, at the end of the 20th iteration, see here, all the values are nearby but not similar, and this is the only one. So we can say that the function has not converged till now. Again, some more iterations are required. And if you see, the convergence iteration number is converging at around nearly 100. Let us see one the same as a MATLAB example over here. Yeah, here, if you see, there are different phases that I have made over here. First phase, I am giving the input parameters. And phase 2, here I am defining the objective function. And phase 3 is the generate initial population. And the cuckoo search main iteration loop starts in the phase 4 with the Levy flights, where the new generated solution will be taken. And we will be checking the bounds, whether the new solution is lying between. In that previous case, what we have seen is, it will be lying between -5 to 5. Okay. Likewise, and in the phase 5, we will be replacing the worstness with the probability PA. Again, generate the new solution, and again, check the solution whether it is between the given range, that is -5 to 5. Again, perform the greedy selection, memorize the best solution, plot the result. So initially, I have taken it as the lower bound here, and upper bound is 5. And I have taken 20 iterations over here, 20 population size, where n equal to n, and the probability discovery rate is chosen as 0.25. And the maximum number of iterations I have taken it here as 100, because it will converge. Anyhow, why I have taken it as 100 is, at the iteration 20, I have seen that most of the values are nearby. It may take 5 more times, 20 to 5 like that. I have taken 100 over here. And I have not defined the objective function over here. I have defined it as a function. That's why I have written it in our last step of the MATLAB function. You need to write like this. So here the function is x1 square minus x1 x2 plus 2 x2 square plus 2x1 plus 4x2 plus 3, what we have defined in the previous case. So this is the one, and now I have generated the first nest with the probabilities, and after that I have taken the sigma values and I have defined the cuckoo search, and again I have identified the best one using these two, and again I have updated the checked with the bounds over here, and I have performed a greedy selection. After that again I have chosen the best one and have replaced the existing nest with some probability using the PA value, and I have taken the step size again. Again I have checked the bounds whether it is within the given limits or not, and I have checked the greedy selection and I have memorized that one with the optimal value, then have plotted it. Now let us see what is the output that I am getting over here. And if you see clearly, this is the convergence function that I have achieved. So if you clearly see, it is starting at some other value, and after 40 at the 40 iteration also it does not converge, slight glitch is there, and after that it is slowly converging and the minimum value is achieved. It is approximately 6.34 somewhere else, and now let us see what is the actual fitness value that we have achieved there. So by typing over here, I will show now. So this is the one. So actually we have seen that it is 3.5 somewhere else, 6.35 below that one. So we'll be selecting the minimum of all these things. So the minimum here is 6.2987. Yeah, 6.0556 is the minimum of all. Okay, this is the new fitness function that has been calculated, and we have minimized for all those things. Okay, so this is how you are going to calculate the for that function, right? So now there is another algorithm that is called as Mech-Kaloch algorithm. One minute. That Mech-Kaloch algorithm is we are using the Mantena's algorithm, that is two normally distributed stochastic random variables to generate a third random variable which has the same behavior of the Levy distribution for large values of the random variable. So here it applies a nonlinear transformation to let it quickly converge to a Levy stable distribution. Okay. So here the simplified version is that we need to write down that is the step size is identified as, this is Mech-Kaloch algorithm. This is Mech-Kaloch algorithm. This is the modified version of the cuckoo search algorithm. So here, this algorithm is said to be the simplified version and does not apply with the nonlinear transformation. It uses the entry-wise multiplication of the random number so generated and distance between the current solution and best solution obtained so far as a transition probability to move from the current location to the next location to generate Markov chain of solution vectors. However, PSO also uses the concept of the local best. Implementation of the algorithm is very efficient with MATLAB, but this reduces the running time. So the algorithm with taking one by one solution from the initial population, then replacing it by the new vector. So how it is replaced is step size. So we will be writing the step size here. Step size equal to 0.01 multiplied by V dot star S, another random variable, minus current best, that is S minus current best. So the new solution will be old solution plus step size into Z, where V is the Mantas algorithm, which is calculated from 3 by 2 normally distributed stochastic variable. So the McCulloch algorithm is based on the explicit formulation to generate random numbers from a Levy process as a function of the two independent variables W and phi psi with uniform distribution in the range of minus pi by 2 to pi by 2. And this is the latest version of the modified cuckoo search algorithm, where you can apply it for better solution when compared to the cuckoo search. So this has been observed to be the benchmark when compared to the existing cuckoo search algorithm. And this cuckoo search algorithm is applied on various applications like that of 4G, where you will be applying on a particular selection of the nodes and to improve the throughput and to reduce the latency. That has been considered as one of the objective function there. So to maximize the throughput and to minimize the latency level, that is being taken as the objective function there. So considering next one, let us see one more example on in the MATLAB. Mira. Then so you can clearly see here the modified search algorithm that is being developed here. Here. So they have taken this one and I have applied this to an image where it is quickly converging when compared to the PSO or cuckoo search. And I have observed this to be better when compared to the cuckoo search, because there the complexity is reduced. We are generating two random numbers to generate a third random number there, but it is been changed over here, and we achieve a better segmentation when compared to the cuckoo search. From this image you can observe that one. I will show the image right now. This is the image. So you can see clearly the better segmentation is achieved, and at a faster rate. The convergence is also faster when compared to the cuckoo search, right? So based on these things, based on these two algorithms, what we have seen till now, these are evolutionary algorithms where the convergence function entirely depends on the set of initial parameters that are being defined, and they are not dependent on the fitness function or the variables that are depending. So it is entirely dependent on these random variables, which is very much faster and easier when compared to the existing benchmark techniques. Okay. Thank you for giving me this opportunity. And any doubts are there, you can ask me.
Thank you for giving such a brainstorming session titled Bio-Inspired Algorithms for Optimization. So I hope all the participants you have enjoyed more in terms of in this regard. Please be asked any questions you are having, any doubts you are having, please ask now. Please raise your questions now. That expert is ready to answer your questions. Please post your questions on the stage. Is there any doubts? Participants, please. I hope the session will be very much clear. That's why there is no doubts from the participants. So,
good morning, sir.
Yeah.
Good morning, sir.
I am Somani from Savara College of Technology. Sir, actually, this even though there are so many bio-inspired algorithms that are there for optimization, but you chose very important algorithms and you gave very insight knowledge on those algorithms. Thank you, sir. Just I want to appreciate the speaker, sir. Thank you very much, sir.
Hello. Sir.
Thank you, participants, for participating in this wonderful session titled on Bio-Inspired Algorithms for Optimization. Now we can leave for lunch. After lunch, around 2 o'clock, again we will meet for a next session handled by Dr. N. Alivelu Manga, Professor of EC, CBIT Hyderabad. There also you can get some ideas and inducements from inducements related to that optimization techniques, which is related to the VLSI technology. We can implement the optimization technique into any area. So it's not limited, it's not confined to that VLSI. She is an expert of VLSI. That's why we have framed the title like that. So be part in that. You can get, you can enrich your knowledge in that area of optimization. So we can leave now. Again, we will meet around 2 o'clock in that same link. Thank you very much. You can leave now.